mentioned we mentioned briefly last time that only square matrices have an inverse, but not all square matrices have an inverse. So let's begin by just mentioning a few basic notes about identity matrix and inverse matrices before we actually see how we can find the inverse of a matrix. Okay, the first thing we want to mention as a note is that the inverse of a matrix, let's call it A, is denoted as the matrix A inverse. So this -1 in the upper right corner is not a power, it's just a label. It's how we label the inverse of any matrix. So that's the first thing we want to mention. And again, for the sake of your notes, let me write this down, that only have inverse, and not all square matrices have an inverse. Okay, so suppose then if a matrix does have an inverse, then what about it? So let's give a note on that. If matrix A has an inverse, matrix A inverse, if that's true, then this is what we can say about the relationship between those two matrices. So A times A inverse is equal to A inverse times A, so the order doesn't matter, and equals the I, or the identity matrix. So let's just say that, let's describe I. So I is the any identity matrix. So if these two matrices that are inverses of each other are 2 by 2 matrices, then the identity matrix will be a 2 by 2 matrix as well. If these two matrices are 3 by 3, then the identity matrix will be 3 by 3. So just a reminder, we've mentioned this in the previous section, but just to complete these series of notes, the identity matrix looks like this, or like this, or so on. So if it's a bigger matrix, if it's a 4 by 4 matrix, then it's going to be a 4 by 4, but it's going to look exactly the same. All the diagonals are going to be 1, and the numbers above and below that diagonal are going to be 0. Multiplying any matrix by an identity matrix is as if you multiply a number by 1. So you get that same number back. 5 times 1 is 5, 3 times 1 is 3, 10 times 1 is 10, so it would be the same way with the identity matrix. So we can say that the identity matrix times any matrix is equal to that matrix times the identity matrix, which means the order of multiplication does not matter in this case, and that is equal to A. Right? So we're multiplying matrix A by the identity matrix, and we get that same matrix back. Okay. So now we can use this formula that if you have a matrix and somebody claims that this other matrix is an inverse of that, then the way you can prove the claim or disprove the claim is just take the product of those two matrices and see if you get the identity matrix. If you do, then the claim was correct, and the original matrices were inverses of each other. But if you don't get the identity matrix, then the original claim is disproved, and these two original matrices were not inverses of each other. So let's see how that works with an example. So in this example, we want to show that this matrix is the inverse of this matrix. Okay, so when we want to prove this, we're going to multiply these two to see if we're going to get the identity matrix. Now, in which order we multiply these two, it doesn't matter. If any two matrices are inverses of each other, this is one of the exceptions, then the order in which we multiply them to get the identity matrix does not matter. But you recall from section 3.2, when we multiply matrices, that order in which matrices are multiplied is very important. But in this case, this is an exception, so it doesn't matter in which order we multiply these. We should get the identity matrix if, in fact, they are inverses of each other. So let's see if we're going to get the identity matrix. So I'm just going to organize these along one line. So 1, 3, 3, 1, 4, 3, 1, 3, 4 times this matrix. You can reverse this multiplication on your own on a scratch paper, and you'll see that you'll get the same result. Like that. Okay. So we remember from the technique to multiply two matrices is that we take the first row, then we multiply it by each of the columns and add those numbers, and then we multiply this first row by the next column, and then when we're done with that, add those numbers and multiply the first row by the next column, or the last column in this case. When we run out of columns, that's when we switch to the next row, and so on. Okay. I think I can fit all that here. So 1 times 7, 3 times -1, right? Plus 3 times -1, plus 3 times -1 again, Then the next column, right? Multiply this by the second column. 1 times negative 3. 3 times 1. 3 times 0. And the next column, this, multiply by this last column. So we'll have 1 times negative 3 plus 3 times 0 plus 3 times 1. Okay. Like that. Okay, so now we ran out of columns, so we're going to move to the second row here. We're going to multiply this by each of these columns and add the numbers as we go along. So 1 times 7 plus 4 times negative 1. By the way, this is a good point where you should, I think, pause the video, do this multiplication on your own, and then come back to the video. And then plus 3 times negative 1. And then we move to the second column. 1 times negative 3 plus 4 times 1 plus 3 times 0. And then the next column, 1 times negative 3 plus 4 times 0 plus 3 times 1. Okay, so we ran out of columns again. That's when we move to the next row, or in this case the last row, and repeat the same procedure. 1 times 7 3 times negative 1 plus 4 times negative 1. Then the second column, so 1 times negative 3, 3 times 1, plus 4 times 0. 1 times negative 3, plus 3 times 0, plus 4 times 1. Okay, so if the two are inverses of each other, we should get the identity matrix. So let's see if we get 1 in this spot. 7 minus 3 is 4. 4 plus negative 3 is definitely 1. So far so good. We should get a 0 in this spot then. Negative 3 plus 3 is 0. 0 plus 0 is 0. Good. So minus 3 plus 0 is minus 3. Plus 3 is 0 again. And that is good so far. So 7 minus 4 is 3 plus negative 3, that's 0. Negative 3 plus 4 is 1. 1 plus 0 is 1. Negative 3 plus 0 is negative 3 plus positive 3 is 0. 7 minus 3 is 4. 4 plus minus 4, that's 0. Negative 3 plus 3 is 0. Plus 0 is 0 again. Negative 3 plus 0 is negative 3. Plus 4 is positive 1. So we definitely got the identity matrix. Okay, so the original matrices, these two matrices are definitely inverses of each other. So we've proved that. We've showed that the claim is true. So now that we've discussed some basic ideas about inverse matrices, and we've shown how we can prove the claim that two matrices are inverses of each other, then how do we find the inverse of a matrix? Now there are at least half a dozen or more, maybe even a dozen, different ways of finding the inverse of a matrix. But in my opinion, the best of those methods, and it's my favorite method of finding the inverse of a matrix, is discussed in this course. And it's my favorite method because once you know how it works, you will not forget it that easily. The other methods will give you the correct result, but if you don't work with the method, you will forget how the procedure works. They are highly procedural, and this method is also procedural, but it's much easier to remember a year down the road than the other methods. Okay. So let's begin that with an example. Suppose we want to find the inverse of the following matrix. Let's start easy with just a 2x2 matrix, a small one. Now, I have prepared a PowerPoint set of slides on the two topics that I've shown to present difficulty to people. Those two topics, one of the two topics is this one, finding the inverse of a matrix. The second topic is the application of the simplex method to solving the maximum problem, which is a topic we will look at in section 5.1 and 5.2. So the PowerPoint set of slides are already on Canvas, so you can start looking at it after today's lecture, because the first 71 slides, I believe, the first 71 slides discuss examples of finding the inverse of a matrix. So the examples that I have in the PowerPoint are dynamic, so they are meant for you to launch the slides in slideshow mode. That way the answers are hidden from you until you've had the chance to project your own solutions on a piece of paper. Then with the PowerPoint slides, you can hit the arrow button in slideshow mode to see the answers that I have on the slides. So after today's lecture, please, in addition to completing the homework and reading the lecture notes carefully or watching the video, please make sure that you look at those first 71 slides in the PowerPoint file that I have posted on Canvas. And if you have any trouble finding it, please let me know via an email. Okay, so we want to find the inverse of a matrix. The way this procedure works is, first of all, we create a split matrix. So we have this. We create a split matrix with the identity matrix for this side on the other side. So 1, 0, 0, 1, like that. Now our objective is to make the left side look like the identity matrix, or match the identity matrix on the left. And when we achieve that on the left side, whatever we have on the right side, it's going to be the inverse of the original matrix. Okay, so you've done this before, right, with the Gauss-Jordan method. So we sweep column to column, and in each column, our objective is to find the diagonal one first. All right, so in this case, we can start with this as it is. We could, if necessary, we could interchange rows if that would help us in any way, but in this case, it doesn't make any difference. So all we need is a 1 in this spot. Well, we can multiply that whole row 1 by 1/3, right? Like that. So we get 1, multiplying this row by 1/3, we get 1 there, we get 7/3 next, and then we get 1/3 in that spot, we get 0 there, and the second row stays as it was before for now. Okay, so again, compare this with this. We want the left side to match the identity matrix. So we want this 2 to become 0. At this point, from the previous discussion of the Gauss-Jordan method, you know that the pivot row is the first row, right? This is the pivot row. And it is the pivot row because we just got the diagonal 1 for that column, and it is in the first row. So the importance of that is that we should use the pivot row to get the 0 in this spot. Well, how can we get a 0 in this spot? Very easily, by adding a -2 to this, we can get a 0. But where is the -2 going to come from? It's going to come from multiplying the pivot row by -2 and adding it to the second row. So let's do that. So row 2, because we're changing row 2, right, equals -2 times row 1 plus row 2. Okay, so let's write down the next matrix. So the first row is not changing because it's the pivot row. -2 times this plus -2 times 1, -2, plus 2, 0. We're just doing this row operation. -2 times 7 over 3, it's -14 over 3 plus 5. So let's do a little common denominator thing here. -14 over 3, that's -2 times that, we get -14 over 3 plus 5. So the common denominator is going to be 3. Now this one, it's already there, so we don't need to multiply this fraction by anything. But the denominator of 5 is 1, so we definitely need to get this 1 to become 3. How do we do that? By multiplying the numerator and denominator by 3. Okay, so we get from the first fraction, we have -14. We didn't have to multiply this by anything because the denominator is already there. It's the common denominator. This one plus 3 times 5, 15, and of course 3 times 1 is 3, which is the common denominator. Okay, so we have 1 minus 14 plus 15 is 1 over 3, and that's what we will enter in this spot. Okay. Now the next one, we want to multiply -2 by 1/3. That's -2/3 plus 0, and that's -2/3. -2 times 0 is 0 plus 1, 1. Right? So you can still see it on the screen. Our objective is to get the left side to match the identity matrix, and when we achieve that, whatever we have on the right is going to be our inverse matrix. But we're not there yet. We've gotten the first column. We're going to move to the second column and get the 1 and then the 0, and then we'll see what we have on the other side. Okay, so to get this 1, what should we do? What row operation would we have to use? Well, if you said multiply the second row by 3, you're absolutely correct. So row 2 is equal to 3 times row 2. That's going to give us 1 in that corner. Okay, let's write the next matrix. The first row isn't changing. The second row is changing according to this row operation. 3 times 0 is 0. 3 times 1/3 is 1. 3 times -2 over 3 is -2. 3 times 1 is 3. Okay, so we got the 1 in the second column. Now we worry about converting this number to 0. Well, you should ask yourself now, which row is the pivot row? And if you answered the second row, you're absolutely correct. So it is the second row is the pivot row because we have just gotten the diagonal 1 for the second column, and that diagonal 1 is in row 2. So that makes the second row the pivot row. What is the significance of that? It's significant because in order to get 0 or convert 7/3 to 0, we need to use the pivot row. So let's do that. How are we going to get a 0 in this spot? We can add a negative 7/3 to this and get a 0. But where is the negative 7/3 going to come from? It's going to come from multiplying the pivot row by negative 7/3 and adding it to the first row. So let's do that. Row 1, which is the row we're going to change with this row operation, is equal to negative 7/3 times row 2, which is the pivot row, plus row 1. Okay, so let's carry out the row operation and find the next matrix. So negative 7/3 times row 2, that would be negative 7/3 times 0 is 0, plus 1, 1. Negative 7/3 times 1 is negative 7/3, plus positive 7/3, that's 0. Negative 7/3 times negative 2, that's positive 14/3, plus 1/3, what do we get? Positive 14/3 plus 1/3. The denominators are already equal. That's great, so we write it down. 14 plus 1 is 15. 15/3 is 5. So we get 5 in this spot. Then we continue with the last one. Minus 7/3 times 3, that's negative 7, right? The 3 and 3 cancel, we get negative 7. Plus row 1, which is 0 in that spot, we get negative 7. Okay, and the second row stays as it was because it is the pivot row. So compare this with the identity matrix. We have achieved our goal of converting the left side to the identity matrix. Therefore, whatever we have on this side is the inverse matrix. So the inverse matrix in this case is equal to 5, negative 7, negative 2, 3. So a good exercise on your own right now as you watch the video is to pause the video and multiply this by the original matrix, by this one, 3725, and see if you're going to get the identity matrix. This is just to verify the work that we just did. You can do that on your own. It would be a good exercise if you did. Okay. Let's move to another example where we're going to find the inverse of a matrix of a 3 by 3 matrix, so a bigger matrix. So we want to find the inverse of matrix A, which has these elements: 1, 1, negative 1, 2, 1, 1, 1, 0, 1. Okay. So it would be good if you pause the video at this point, or review if you don't know where to start to answer this question. Review or rewind the video back to the previous short 2x2 example we just did. Watch it from the beginning to the end, because this applies to that even though this is a bigger matrix. The procedure is exactly the same. Review that method, then come back to this. I want you guys to get used to writing down your own solution before looking at anybody else's solution. If you do this in any quantitative course you're taking, whether it be at this one, accounting, economics, finance, marketing, you'll be very competent in that subject. But you've got to get used to writing down your own solution first. Okay, so I trust that you'll do that before you see my solution, and then hopefully that'll help you master this procedure. All right, I'm assuming you've done that, and now you're back ready to see my solution, which would be great. Okay, the first thing we should do is we will create the split matrix with the identity matrix on the other side. Like that. Okay, so our objective is to convert the left side to the identity matrix, and once we've achieved that on this side, whatever we have on this side is the inverse matrix of this original matrix. Okay, so, and we sweep column by column, right? Now, our first objective is to get a 1 in this corner. We already have that. That's fantastic. So now we can focus on obtaining or converting these two numbers to 0 to match this first column on the other side. Okay, at this point, which row is the pivot row? If you answered row 1, you are absolutely correct. The first row is the pivot row because it contains the diagonal 1 in that column. Okay, so we're going to use the pivot row to convert the 2 and 1 to 0. Let's write down the row operations for accomplishing that. To convert the 2 to 0, we can do row 2, because we're changing row 2, right? Row 2 is equal to minus twice row 1 plus row 2. How are we going to get this 1 to convert to 0? All we need is to add a negative 1 to it, right? But where is the negative 1 going to come from? It's going to come from multiplying the first row by negative 1 and adding it to the third row. So row 3 would be equal to minus row 1 plus row 3. So this minus row 1 is equivalent to multiplying the first row or the pivot row by negative 1 and adding it to the third row. Okay, let's write down the next matrix. The first row isn't changing because it's the pivot row. The second row is going to change according to this row operation. Minus twice the row 1 and then plus row 2. Minus 2 times 1 is minus 2. Plus 2, 0. Minus 2 times 1 is minus 2. Plus 1, negative 1. Minus 2 times minus 1, that's positive 2. Plus 1, 3. Minus 2 times 1 is minus 2. Plus 0, minus 2. Minus 2 times 0 is 0. Plus 1 is 1. Minus 2 times 0 is 0. Plus 0 is 0. Okay, we're done with this row operation. We're going to move to this one. This is saying multiply the first row by negative 1 and then add the result to row 3. So minus 1 times 1 is minus 1. Plus 1 is 0. Minus 1 times 1 is minus 1. Plus 0 is minus 1. Minus 1 times minus 1, it's positive 1. Plus 1 is 2. Minus 1 times 1 is minus 1. Plus 0, that's minus 1. Minus 1 times 0 is 0. Plus 0, it's 0. Minus 1 times 0 is 0. Plus 1, it's 1. Okay, so compare this with the identity matrix here. Are we done with the first column? Yes, they match, right? So we're going to move to the second column. In doing that, our objective is first get the 1. Get the negative 1 to convert to 1. Then we're going to worry about these two numbers in the same column and converting them to 0. So how can we convert the -1 to 1? Very easily, right? If you wrote down on your own paper, just multiply the second row by -1, you're absolutely correct. So row 2 is equal to minus row 2, which means -1 times row 2, right? This is just a distributive property. Okay, so let's write down the next matrix. The first row and the third row don't change, so we're going to write them down as they are. And then here it is, I'm at the second row, so -1 times this whole row. -1 times 0 is 0. -1 times -1, 1. -1 times 3, -3. -1 times -2, +2. -1 times 1, -1. -1 times 0, 0. And the third row, we can write it as it is, like that. Okay, so our objective is to get this column to look like this, right? 0, 1, 0. So we already got the 1. So our pivot row is row 2, right? Because that's the row that contains the diagonal 1 that we just got. So that's the pivot row. So we're going to use the second row or the pivot row to convert the 1 and -1 to 0. How are we going to convert this 1 to 0? Well, all we need is add a -1 to this, and we're going to get it to be 0. Where is the -1 going to come from? It's going to come from multiplying the pivot row by -1 and adding it to the first row. So the row operation would be row 1, because we're going to change row 1 with this row operation. So row 1 equals minus row 2, or -1 times row 2, plus row 1. How are we going to change the -1 to 0? Well, all we need is to add a +1 to this, and we're going to get it to be 0, right? Where is the 1 coming from? In this case, we can simply add the pivot row to the third row, because this is already +1. So just add the pivot row to the third row, and we're going to get a 0 in that spot. So we have row 3, which is the row we're changing, right? The -1 we're converting is in row 3. So row 3 equals row 2, which is the pivot row, plus row 3, which is the row where we are changing. I hope you're following all of this. If not, please type your question right underneath the video on the discussion board. That way, if others have the same question as you, once I answer your question, they'll get their answers as well. Okay, so let's apply these two row operations and write the next matrix. First, we're going to do this one. Multiply the second row by -1 and then add it to row 1. So -1 times 0 is 0, plus 1, 1. -1 times 1 is -1, plus 1 is 0. -1 times -3 is +3, plus -1, that's +2. -1 times 2 is -2, plus 1, -1. -1 times -1, that's +1, plus 0 is 1. -1 times 0 is 0, plus 0, it's 0. Now the second row was the pivot row. It's not changing, so let's write it down as it is. Now the third row, we're going to do this row operation, right? So this is saying simply add the pivot row, which is row 2, to row 3. Great, so let's do that. 0 plus 0, 0. 1 plus -1, 0. -3 plus 2, -1. 2 plus -1, 1. -1 plus 0, -1. 0 plus 1 is 1. Okay, so now if I quickly move this down, or I don't have to do that actually, you can see it right here. Our objective is, we're done with the second column. Now our objective is to convert this to becoming 0, 0, 1. So we start with the diagonal 1 first, make sure that that is equal to 1, then we worry about the zeros in that column. Well, how are we going to convert this -1 to 1? Very easily, I'm sure you all see it by now. Simply multiply the third row by -1. So row 3 is equal to -1 times row 3. This is just distributive property, right? -1 times row 3. Great. So let's write down the next matrix. The first two rows don't change, for now at least. So we're going to write them down as they are, like that. Now multiply this whole third row by -1, so 0, 0, 1, -1, +1, -1, right? And now we're going to worry about converting the -3 and 2 to 0. Before we do that, which row is the pivot row at this point? Well, if you said row 3, you're absolutely correct. The reason is we just got the diagonal 1 for that third column, and that diagonal 1 is in the third row. So this is our pivot row, which means we need to use row 3 to convert the -3 and 2 to 0. Okay, so let's write down the row operation for accomplishing that. Row 1 is equal to, all we need is a -2, so we can add it to this 2 and get 0, right? Where is the -2 going to come from? Multiplying the pivot row by -2 will give us that, and we can add it. So -2 times row 3 plus row 1. It's going to give us that. Now to get this -3 to be 0, all we need is to add a +3 to it. Where is the +3 going to come from? It's going to come from multiplying the pivot row by 3 and then adding it to -3. So row 2, which is the row we're changing as we change the -3 to 0, is equal to 3 times the pivot row, or 3 times row 3, plus the row we're changing, which is row 2. Okay, so let's write down the next matrix. I think I can fit it right here at the bottom. Barely, but it'll fit. Okay, so we're going to do this row operation first. -2 times row 3 plus row 1. So -2 times 0 is 0 plus 1, 1. -2 times 0 is 0 plus 0, 0. -2 times 1 is -2 plus 2, 0. -2 times -1 is +2 plus -1, +1. -2 times 1 is -2 plus 1 is -1. -2 times -1 is +2 plus 0 is +2. Okay. Row 2 is changing according to this row operation, which is multiply the third row by 3 and add it to row 2. Okay, so let's do that. 3 times 0 is 0, plus 0, 0. 3 times 0 is 0, plus 1, 1. 3 times 1 is 3, plus -3, 0. 3 times -1 is -3, plus +2, that's -1. 3 times 1 is 3, plus -1 is +2. 3 times -1 is -3, plus 0 is -3. And the third row is the pivot row, so let's write it down as it is. So take a look on the left side. It's the identity matrix, right? So we are done, which means this matrix is the inverse of the original matrix. So A inverse is equal to 1, -1, 2, -1, 2, -3, -1, 1, -1. Okay. Well, I hope that this helped you fully understand how we find the inverse of a matrix, and if somebody claims that two matrices are inverses of each other, how do we prove or disprove that claim? With that, we have wrapped up section 3.3. When we come back next time, we will begin with section 4.1. Until next time, thanks for joining me and have a nice and safe day.